Good morning. The ideas that we will develop in this section are based on the notion of divisibility. Division of an integer by a positive integer produces a quotient and a remainder. Working with these remainders leads to modular arithmetic, which plays an important role in mathematics and which is used throughout computer science. Division. Definition 1. If a and b are integers, with a not equal to 0, we say that a divides b if there is an integer c such that b is equal to ac. When a divides b, we say that a is a factor of b and that b is a multiple of a. The notion of a vertical bar b, which is pronounced a divides b, denotes that a divides b. We write a doesn't divide b when a does not divide b. Example 1.1. Determine if 3 divides 7. Solution. If 3 divides 7, then there's integer c such that 7 is equal to 3c. Solving for c is equal to 7/3. However, since 7 is a prime number, there can be no integer where c is equal to 7 divided by 3 unless the denominator is either 1 or 7. Since 3 is not an element of the set 1 or 7, there is no integer c, and hence 3 does not divide 7. Determine if 3 divides 12. Solution. If 3 divides 12, then there's an integer c such that 12 is equal to 3c. Solving for c equal 12 divided by 3, we find that it's 4. Hence, 3 does divide 12. Example 2.1. Let n and d be positive integers. How many positive integers not exceeding n are divisible by d? Solution. The positive integers divisible by d are all the integers of the form dk, where k is a positive integer. Hence, the number of positive integers divisible by d that do not exceed n equal the number of integers k with 0 less than dk less than or equal to n, or with 0 less than k less than or equal to n divided by d. Therefore, there are the floor of n divided by d positive integers not exceeding n that are divisible by d. Example 2.t. How many integers not exceeding n equal 28 are divisible by 4? Solution. Find the floor of 28 divided by 4, which is 7. Theorem 1. Let a, b, and c be integers. Then if a divides b and a divides c, then a divides the sum of b plus c. 2. If a divides b, then a divides bc for all integers c. 3. If a divides b and b divides c, then a divides c. Corollary 1. If a, b, and c are integers, such that a divides b and a divides c, then a divides the quantity mb plus nc whenever m and n are integers. The division algorithm. Let a be an integer and d be a positive integer. Then there are unique integers q and r with 0 less than or equal to r less than d, such that a is equal to dq plus r. Please note in this discussion that r is a non-negative number. That is the remainder. Definition 2. In the equality given in the division algorithm, d is called the divisor, a is called the dividend, q is called the quotient, and r is called the remainder. This notation is used to express the quotient and remainder. Q is equal to a div d, and r is equal to a mod d. Example 3. What are the quotient and remainder when 101 is divided by 11? Recall, a is equal to dq plus r, where a is 101 and d is 11. Q is equal to a div d is equal to 101 div 11 is equal to 9, and r is equal to a mod d, 101 mod 11 is equal to 2. To check, a is equal to dq plus r, 101 is equal to 11 times 9, 99 plus 2 is 101. Example 4. What are the quotient and remainder when minus 11 is divided by 3? Q is equal to a div d, minus 11 div 3 is minus 4. R is equal to a mod d is minus 11 mod 3. Minus 11 minus 3 times minus 4 is equal to minus 1, minus 12 is equal to 1. A is equal to dq plus r minus 11 plus 3 times minus 4 plus 1. Recall that 0 is less than or equal to r is less than d, equals 0 less than or equal to r less than 3, therefore r not equal to minus 2. Modular arithmetic. Definition 3. If a and b are integers and m is a positive integer, then a is congruent to b modulo m if m divides a minus b. We use this notation. A is congruent to b mod m to indicate that a is congruent to b modulo m. We say that a is congruent to b mod m is a congruence and that m is its modulus. The plural of modulus is moduli. And if a and b are not congruent modulo m, we write a is not congruent to modulo, a is not congruent to modulo m. Theorem 3. If let a and b be integers and m is a positive integer, then a is congruent to b modulo m if and only if a mod m equal b mod m. 5.1. Determine whether 17 is congruent to 5 modulo 6. 17 is congruent to 5 modulo 6 equals 6 divides 17 minus 5 equals 6 divides 12. 6 divides 12 implies that 12 is equal to 6c, c is equal to 2. And yes, 17 is congruent to 5 modulo 6. Example 5.2. Determine whether 24 is congruent to 14 modulo 6. Solution. 24 is congruent to 14 mod 6 equals 6 divides 24 minus 14 equals 6 divides 10. 6 divides 10 implies that 10 is equal to 6c. c is equal to 10 sixths. There is no integer equal to 10 divided by 6. Hence, 24 is not congruent to 24 mod 6. Theorem 4. Let m be a positive integer. The integers a and b are congruent modulo m if and only if there is an integer k such that a is equal to b plus km. Theorem 5. Let m be a positive integer if a is congruent to b mod m and c is congruent to d mod m, then a plus c is equal to b plus d mod m and a times c is equal to b times d mod m. Show that if 18 is congruent to 3 mod 5, given 7 is congruent to 2 mod 5, and 11 is congruent to 1 mod 5. Solution. By theorem 5, a plus c is equal to b plus d mod m. If a is congruent to b mod m and c is equal to d mod m, let a equal 7, c equal 11, b equal 3, and d equal 1. Then 18 is equal to 7 plus 11 is congruent to 2 plus 1 is equal to 3 mod 5. Corollary 2. Let m be a positive integer and let a and b be integers. Then the sum a plus b mod m is equal to the quantity a mod m plus b mod m, that quantity mod m. And the product ab mod m is equal to the product of a mod m and b mod m, that product modulo m. Arithmetic modulo m. We can define operations on z subscript m, the set of non-negative integers less than m, that is, the set 0 through m minus 1. In particular, we define the addition of these integers denoted by plus sign subscript m as a plus sign subscript m is equal to a, the sum a plus b modulo m, where the addition on the right-hand side of this equation is the ordinary addition of integers, and we define multiplication of these integers denoted by the dot product sign subscript m as a multiplied by b modulo m as the product of a times b modulo m, where the multiplication on the right-hand side of this equation is the ordinary multiplication of integers. The operations of addition subscript m and multiplication subscript are called addition and multiplication modulo m. And when we use these operations, we are said to be doing arithmetic modulo m. Example 7. Use the definition of addition and multiplication in the integers modulo m to find addition modulo m of 7, or addition modulo 11 of 7 and 9, and the product modulo 11 of 7 and 9. So 7 and 9 modulo 11 is 16 mod 11 is equal to 5, and 7 times 9 is 63 mod 11 is equal to 8. So here's a summary of properties in the modulo m space. Closure. If a and b belong to the integers modulo n, then the sum modulo m and the product modulo m belong to that space. If a, b, and c belong to the integers modulo m, then the associative property over addition belongs to there, and also the multiplicative property applies. Commutativity, if a and b belong to the integers modulo n, then it applies to modular addition, and we also have the commutative property of modular multiplication. The identity elements 0, 1 are identity elements for addition and multiplication modulo m respective. That is, if a belongs to the integers modulo m, then a plus 0 using modular addition is equal to a, and multiplication a times 1 using modular multiplication is equal to a. Additive inverses. If a is not equal to 0 and it belongs to the integers modulo m, then m minus a is an additive inverse of a modulo m, and 0 is its own additive inverse. That is, a plus the difference m minus a, where I'm adding modulo m, is equal to 0, and 0 plus 0 is equal to 0. Distributivity. If a and b and c belong to integers modulo m, then we have the distributive property of multiplication modulo m over the sum, where I did the sum using the modulo m property.